Yeah, well, so thank you very much for the invitation. It's great to have the opportunity of coming here, and thanks for all of you for coming. Some familiar faces, some unfamiliar faces. So I'm going to talk about some work that I've been involved with over the last probably 12 months. It's actually, well, more than that, actually. This was my COVID project. So I remember conceiving of this sort of in March 2020. So basically when the shutdown started happening or when people became aware of it. And it became sort of something I was working on back all the time ever since. So, and it finally got itself published earlier this year. So I'll refer to that as well. I'd like to introduce you to Laura. Laura Anderson is my colleague who really helped me get to the point, get to the story that I'm going to tell. Not the whole of it. Really, the punch. It's really the punchline at the end. But she's a fascinating person to work with. She's at the State University of New York, as it says, and does work in combinatorics topology and oriented matroids, which nobody's ever heard of. You ask mathematicians about that, and they go, "What? What's that?" So she works in a very small area of mathematics, but it turns out to be great relevance to the questions that I'm going to pose, and has helped develop actual answers to those questions. So this is the collaboration I'm most proud of in a way, because and she thinks it's a hoot as well because she gets to work with psychologists. So she thinks that this is applied research for her, whereas this is cutting edge mathematical psychology for us. So it's a bit of fun that way. So that's the first person. The second person I want to introduce you to, and unfortunately I don't have a picture, but some of you may remember, is Frederick M. Lord. There's his dates. And he wrote what I might call the Bible of mental testing, at least for a time. So you have to be a bit of an old person like me to even have heard of Lord. Some of you probably have. Yeah, sure. Yeah. So I remember people used to talk about Lord and Novik's 1968 book quite considerably. So all I'm doing to do is say that Lord is no slouch. He knows a little bit about psychological testing, and he's thought about measurement, thought about what test scores might mean, so forth. And the reason I want to introduce him is because now I'm doing the same thing happening. Oh, I should do that. Maybe press that. There we go. Is that he wrote a paper. You know as well? Okay, right. Yeah. So this is a very cute paper. It's only about a page. It's very easy to read, and it's called Football Numbers, and it's a parable of permissible statistics. Now, I'm going to just say what he says, and then we can reflect on that as we go. So it's a story. So there's a retired psychology professor X who's given the university franchise to sell 2-digit football numbers to be worn by players as a means of identification. Right? So just numbers, stick on the back. And the sophomore and freshman teams each buy 1,600 of these numbers, but later the freshman team complains that the numbers they had bought are too low. And because of that, the sophomore team are laughing at them. Tragedy. So Professor X consults a statistician to see what's going on. The statistician calculates the average of Professor X's football numbers, which turns out to be 54.3, and the standard deviation, which is 16. At this point, Professor X is horrified, throws up his hands, says, "The football numbers are just labels. They're not numbers. You can't do that. You can't add them and divide them. What are you doing?" So those in the know, Professor X is thinking of football numbers as being forming a nominal scale. The numbers are not numbers. And the statistician says, "Well, I just did that." And he says, "The numbers," this is the famous phrase, "the numbers don't know that," he says, or she says. "Since they don't remember where they came from, they always behave just the same way." So you've got to think about that for a minute. I was thinking about that too, saying, what's really going on here? What's really going on here is that numbers, they don't know the way you think about those numbers. You as a analysis or a statistician might have an attitude towards those numbers. Those numbers really represent something else, but the numbers don't know that. They're just sitting around being numbers. So she then calculates the average of the freshman's football numbers, turns out 50.3, and the statistic. So this statistic looks a little bit, it's basically a T statistic. turns out to be 10, and the associated p-value is 0.01 by something called Chebyshev's inequality, which I hadn't heard of, but statisticians know all about this. And it's basically says that the p-value associated with the t statistic is always less than or equal to 1 over t. So it's 10, 1 over 10, p-value is at most 0.01. So it's a thing you can do when you don't want to make any distributional assumptions about your statistic. Anyway, that's a little bit of statistician stuff. And she concludes that it's implausible that the freshman team's numbers are a random sample of Professor X's football numbers. The freshman team are vindicated. Now, the moral of the story, this is my moral of the story, it's not necessarily the way Lord presented it, is that if the question you ask only concerns the numbers before you, they will suffice. If you're going to ask questions about numbers, those numbers are sitting there ready to answer those questions. You don't have to worry yourself about scales or what they represent or anything else that you might have. Now, this turns out to be quite a controversial paper. There's been many other papers written about it, and people gone on about it this way and that way. In fact, the following year, there was an article where someone criticised Lord for this conclusion. So he wrote a kind of follow-up the following year in 1954, which is his response. So he says in very clear terms, the conclusion is that nominal and ordinal numbers, including test scores, may be treated by the usual arithmetical operations so as to obtain mean, standard deviations, and other similar statistics from which, in certain restricted situations, correct conclusions may usefully be deduced with complete logical rigor. Right. Okay. So this is not what is often taught in introductory psychology statistics. People say, oh, it's a nominal scale, it's an ordinal scale. You can't do certain kinds of statistics. And in fact, it relies on work by S.S. Stevens, who has gone, said, well, certain statistics you can calculate for things on ratio scales or interval scales that are not for nominal or ordinal. Lord says, no, that's just rubbish. You can do all those things. If all you're interested in is the numbers, because then he goes on to say, suppose the football numbers are now scores on a perfectly valid intelligence test, as if we hadn't got such a thing. And now consider the following statements. The mean intelligence test score of the freshman group is lower than that of the population. Okay? The mean intelligence of the freshman group is lower than that of the population. The sample of freshmen cannot plausibly be assumed to be a random sample from the population. He says, which, if any, follow from the statistician's analysis? Right. Think about it. All right, so here's the answer. So the first and third are just simply restatements of what the statistician had concluded. The middle one doesn't follow at all, and that's Lord's point. Lord's point is that if you're asking questions about the test scores, the football numbers, then you can do what you like with those numbers. Those numbers are numbers. But if you are now saying those numbers stand for something else, so the test scores stand for something called intelligence, then that's no longer the case, because you don't know what the relationship is between the test scores and something called intelligence. And that's his point. And that, okay, so I'm going to say, spell it out. Intelligence is a construct inferred from the observed measure. Even if we assume that intelligence is a quantity, the relationship between its value and the corresponding test score is unknown. Okay, so let's unpack that slightly. So we have a concept of quantity. Now, a test score, or a football number, is a quantity. It entails magnitude, describing how much of something we have. So we say, if I'm going to assign you the number 10, you have more of something than if you got the number 9. And many observed measures are quantities. So you can get the score on a Raven's progressive matrices test. You can calculate the number of studied items recalled. You can get a score on a Beck depression inventory. You can give people a Likert scale and take an average. These are all quantities. They're expressed as numbers, and the numbers are meaningful. A big number is bigger than a small number. And because they are numbers, they can be manipulated mathematically, added, subtracted, divided, multiplied, squared, exponentiated, submitted to analyses such as ANOVA, all of that's possible. But what you can't do then is draw a conclusion from that to something that number might be taken as representing. So we introduce something I'm going to call, in a very loose way, representational measurement. So there's a whole long history of the term representational measurement, in fact, the representational theory of measurement. But I'm not going to buy into that at this point. I'm just going to use the term. And it occasions when we use numbers associated with an observed quantity to represent an unobserved theoretical quantity. So here's some examples, right? So here's our observed quantities, and so when people give people an intelligence test such as Raven's progressive matrices, they do so because they're not so much interested in the score on that particular test, but because that test tells us something about a theoretical construct like intelligence. And we count the number of recalled items, not because we're interested in the number of recalled items necessarily, but because we're interested in studying memory, some other quantity altogether. And that distinction is very important. And that's the main first point, number one, to sort of get that across. And that leads us to something which Hassop Chang, in a book called Inventing Temperature, calls the problem of gnomic measurement. And David Kellen, with some others, including me, has written a paper on this as well, which you could consult. And the idea is that, as occurs in science, is that you might have a theoretical construct, a quantity, and you're trying to get hold of it in some way by something that you can observe. And there's some kind of relationship between the two. And the problem of gnomic measurement, as discussed by Chang, is we want to measure this quantity X, this intelligence, memory, level of depression, whatever it is. Quantity X is not observable, so we infer X from quantity Y, which is observable. To do this, we need to know the relationship between X and Y, if there's a functional relationship between the two. But we don't know what the function is. But we don't know what the function is because to do so involves knowing the value of both X and Y. If we knew that, then we could work out what the function is. So therefore, we have to measure the quantity X. We're back where we started from. So it's a problem. Now, what was interesting to me in all of this was that I had for a long time assumed that psychology had special problems in measuring some of these constructs, which were sort of somehow hidden and unobserved. Like we don't see memory, we see scores on tests, but we don't see the construct. And what was interesting about reading Chang's book was that this is true also of every part of science. It's not special to psychology. So Chang the title of the book is Inventing Temperature, and he looks at the way in which the measurement of temperature has been developed historically from around 1600 to the end of the 19th century, and with lots of philosophical sides and the like. And so the way to think about this is that you say, well, what we can observe is the level of a thermometric substance, as they say, like alcohol or mercury or water or something that goes up and down as you heat it. And but we can measure that. We can find out how far up and down it goes. But what we're not so much interested in how high a column of mercury is. What we're interested in is the temperature. The temperature is actually a theoretical construct, and we have to work out what the relationship between those two things is. And that took over 200 years to work out, and it turns out to be dependent upon quite sophisticated theory about what temperature is and how that temperature can produce the phenomena that you can measure. Now, we're not in that situation in psychology. So we don't have a solution to this kind of problem, a direct solution. But again, think about it as a problem. Think about how we might solve it. So we can ask now, okay, so that we think about this problem of gnomic measurement. And what are the ways in which it has touched psychology historically? One way is that people just don't care about it. They ignore it entirely. not a thing, not a thing. So I do an experiment. I find I measure the number of words recalled, and then all of my discussion is about memory, right? Just ignore it. Don't even think about it. The other trick is if you're slightly dimly aware of this, you can say, "Oh, I understand that that memory is different from the number of items recalled, but I'm going to define memory operationally as the number of items to recall." Then I do this. Off I go. This doesn't get you out of it, because what it means, of course, is that if somebody else defines memory slightly differently, then you're not talking about the same thing. You can't compare, you can't build science that way, because someone else has made another definition, and we don't know what it is. Oh, I'm using words, you're using faces. They could be completely different things. There's nothing linking the two. So how do we do that? The other thing, well, what we can do to get more sophisticated is to have propose a link function. There's a functional relationship between these two things. Let's just say what it is. Sometimes I'll say it explicitly. I'll say this is part of my theory, that there's a link function of this form. So in signal detection theory, which I'm very familiar with, the link function is very often a normal distribution. Normal cumulative distribution, if you think about it enough. And people will sometimes try and justify a link function, or otherwise just say, oh, we're just going to say this, just to move our numbers from this domain to that domain. So you can do that, but that link function just comes out of thin air. There's no justification for it. It'd be the same as saying, I've got my column of mercury. There's temperature over there. The link function is a linear function. I'm just going to go with that. And there we are. So the other approach is the one that has, I guess, occupied me, and what I'm going to now talk about, is to consider only ordinal information. So this is not trying to. So when we measure our observed variable, we have numbers, right? We can be as fine-grained as we like. But the thing is, what can we do with those numbers? And as I said before, one thing we can do is we can say, well, if I'm giving you a larger number, then you've got more of something than if I've given you a smaller something. And that's ordinal information. And maybe we can pull ourselves up by our bootstraps with just that knowledge. So this leads to the notion of monotonicity, which is that if an observable quantity y can be regarded as a measure of some theoretical construct x, right? So if I'm going to say that the number of words recalled depends upon how much memory someone's got, that's kind of part of my pre-theoretical notion about what memory is, then we expect our observed measure y to be weakly monotonic function of x. So if Alice has more of x than Ben, then Alice's observed value in y should not be less than Ben's observed value in y. If it is, then what are we going to do? We're up the proverbial creek without a paddle. We've got nothing to say. So, and why weakly monotonic is because we might have crazy observed measures like Likert scales, where we only have the numbers, say, 1 to 5. And if we think about that as measuring some kind of attribute or attitude or quantity that varies continuously, then the function will look something like that. And that's a weakly monotonic function, because if someone might, if we put Alice and Ben there, Alice might have more of the strength of the attribute than Ben, but they might have the same score on the Likert scale. Yeah.
So does this assume no error? Because you can imagine violations of this.
Yes.
Yeah.
It assumes no error. So this is completely idealized. So we haven't got to the error part yet.
I'm sorry.
Yeah. So this is all idealized. So, but it's why you to be realistic, you need to have a weakly monotonic assumption, and it's an assumption which enables you to do anything at all. It's if you're proposing a link function, that's what you're doing. You're actually proposing something stronger. So this leads us now to a well-known paper by Jeffrey Loftus from 1978, where he takes this distinction that I've just drawn and draws out the implications it has for data analysis, and particularly the interpretation of interactions. That's the title of the paper. So his point is that some statistical interactions on the observed measure do not imply an interaction on the inferred theoretical construct. So in this particular case, what we have is on the left-hand side is this is if we were God and we knew what was going on, and we have an experiment where we manipulate two factors, A and B, and there's an additive relationship on our theoretical construct, intelligence, memory, whatever it is. And then, but then we say these things can undergo a monotonic function, and by monotonically distorting our axis X, we get our observed measure Y, and we can introduce an interaction that way. And that interaction on the right-hand side, although something that occurs at the level of the observed measure, isn't something that from which you can infer that there has to be interaction in the theoretical construct itself. And Loftus calls that a removable interaction because you can remove it by an appropriate monotonic transform of the data. So those don't allow that inference, but others do. So in this case, we can't actually get, even though I've written it as a monotonic relationship. So if I try and do a monotonic transformation of the theoretical construct, I cannot get that pattern on the right-hand side. And so that pattern on the right-hand side, which sometimes goes by the name of a crossover interaction, he calls a non-removable interaction because I can't get rid of it. It's going to hang around. And so it is inconsistent with an additive relationship. So his point was that if you found interaction of that sort, then it would be something that you could say that there is an interaction in the theoretical quantity as well. So that was his point. That was what he was trying to say. Now, I can say more about that. I won't say more about that. So there was a paper by E.J. Wagemakers and colleagues from about over 10 years ago now, where they looked back to 1978 and had asked whether Loftus' paper had any impact on research practice in the intervening 34 years. And the answer was no, none at all. Had it any impact on textbook content in the intervening years? Were people picking it up and having little chapters talking about this matter in textbooks? And the answer is no. So it's gone nowhere. And so the question is, why has it gone nowhere? So, I mean, one is simple lack of awareness, which obviously if it's not in the textbooks, there's no expectation that people would be aware of it. But also, I think it's because this is the error part coming in. There's no good way of testing whether you have a removable or a non-removable interaction. What's really going on here? So it's all idealized. So you can draw those kinds of figures that Loftus has done and say, oh yeah, there you go. But you've got noisy data. So is that thing really a crossover interaction, or is it something else? Is it this or that? And we don't have a test for it. So that, I think, is what we came up with. So this is why it's entitled monotonic linear regression. This is the name we gave to the approach that we developed. And so I know you're going to read that, but on the right-hand side is some sort of it's artificial data. It's artificial toy example that we used in the paper, and I'm presenting it to you because it kind of looks like a crossover interaction, but there's a lot of error. See the error bars there? Is that sufficiently crossover-y for it to be non-removable or not? And so our approach has been that we take a data set. Now, the data set has to be structured in a factorial design. So we have at least two factors fully crossed. You can have 3, 4, 5, whatever many you like. You can have as many levels as you like. Indeed, the more levels, the better, turns out. But this toy example gives you a sense of it. So the approach is that we say, okay, we've got a design. There's a 2 by 2 factorial design that gives us 4 cell means, 4 numbers that we're playing with. And if you've got 4 numbers, then you've got 4 factorial or 24 different ways like you can arrange them. This one's bigger than this, one's bigger than that, so on. So, but a lot of those arrangements, those permutations, are not consistent with an additive model. So we can work out the ones that are consistent, and it turns out in a 2x2 design that only 8 of the 24 possible orders can occur if the relationship is purely additive. So what I mean by that, so the idea is that if the relationship is truly additive between our A's and B's on our theoretical construct, then if I do a weakly monotonic transformation, I can't change the order of these things. I can make some of them equal, but I can't swap them around. Right? So if it's not one of those 8 orders, then it ain't additive. So what the technique then does is tries to find which of those 8 orders best fits the data, and calculates basically an error measure, fitness measure, so which is nothing more complicated than least squares, weighted least squares, and then you can say, okay, is that number big enough? And that number will now capture the error in the data, because you can then do a bootstrap test of that number to see whether it is statistically significant. And folks a lot smarter than me will no doubt come up with some kind of Bayesian way of doing this. I keep trying. People always ask that question: is there a Bayesian way of doing this? I say, yeah, knock yourself out. I'm sure there is. Let's see it. I'm sure you can do it. The interesting thing. So let me just take you through that. So the idea is that here's what ANOVA does in this case. So what ANOVA does is, of course, as we all know, is it just fits little submodels to the data. So, and I've highlighted the additive one, which doesn't always, normally in a variance table like this, you have the main effects and then the interaction. People don't worry about the additive model, but sometimes that is an interesting question to ask. So you can do that. And in fully factorial designs, equal n, everything nicely, homogeneity, variance, it all works out very nicely that you can simply sum the sums of squares. And you can see that you get an F ratio in this case of 2.65, which tells you that, well, if you want to be nice and frequentist about it, you don't have the additive model doesn't it can't be rejected, but the interaction is the additive model can be rejected, and the interaction can't. There is a significant interaction. I say that. So what I've got over there, of course, is the data in black, and when you're fitting an additive model, that's the model you're fitting. That one, right? So that's the best fitting additive model that you can calculate. But that's great if all you're interested in is the thing that you just measured. This is Lord's point. If that's what you're interested in, great. You can talk about these effects and you can draw inferences about the thing that you just measured. If you're trying to make an inference beyond that to some theoretical construct, which is now weakly monotonically related to that, then that's no longer the case. You have to do something else. So this is the MLR analysis of this. It turns out that the main effects turn out to be the same. And there's a mathematical reason for that. But now what's happened is that the interaction term that is large in the ANOVA is no longer is reapportioned here. Right? Because this monotonic distortion that we're imagining is happening, ANOVA thinks that's an interaction that goes into the interaction basket, whereas the ordinal analysis says no, that's all great. That's part and parcel of what the additive models is telling us. And over there, you can see the kind of model that is being fit. So from ANOVA's point of view, that's a huge interaction that we're fitting. But in fact, from an ordinal point of view, that's an additive model, but one in which you've got this weakly monotonic transformation that's taken this additive relationship and put it into this thing that looks like an interaction. And you can see that when I said earlier about Loftus was saying that a non-removable interaction is a crossover interaction, you can see we're right on the edge of being a crossover interaction. Right? We're right on the cusp of that. So if we move that point up a little bit, it will crossover. So, but that's what weak monotonicity buys you, puts you on that edge. And And the conclusions you reach are now quite different. Now the additive model is significant, right? So and the interaction term is no longer significant. So you would make a different set of conclusions, not about the data, but about what you're inferring from the data in terms of your theoretical construct. Now, where are we going? I don't know how we're going. So what can we do with this? Well, we can test for higher order interactions. So if we have a design with, say, 3 factors, then you've got your 3 main effects. You've got your pairwise interactions, and you've got your triple interaction. You can test those pairwise interactions. Those pairwise interactions also, define a set of orders that are consistent with them. And what I've done is I've suppressed all that hard work. And this is where Laura, who I introduced you at the beginning, comes in. So she gives us the way in which we can take a design matrix and work out of all the possible orders, which ones are consistent with that particular design matrix. And that can include interactions. We can also, if you have enough data, you can obtain an estimate of this weakly monotonic link function, right? So rather than assuming what it is, you can actually calculate it, look at the shape of it. And I think we've discussed, I think, some of that with recognition memory, showing that at least for a lot of data, that it has a pronounced skew. So the assumption that it's a symmetric normal distribution is challenged, let's say, by this analysis. And you can also identify scale values. So these are the effect sizes. But you can get estimates then of what the effect of A is, what the effect of B is, or whatever it is like that. The toy example, the 2x2, is not particularly good at that because there's not a lot of constraints. But if you get up to, say, I don't know, 5 or 6 by 5 or 6, which can happen in the kinds of designs that you do for recognition memory experiments, then there's a lot of constraints, and you can get very good estimates of these things, and simulations show that you recover it quite well. So I'll finish. So the nomic measurement problem is a real problem in psychological science that can't be absorbed. That's probably what I tried to convince you of. The only justifiable solution is based on the assumption of monotonicity. So this is a bugbear that I have. So when you read, you do your little thing about where you learn about Stevens's nominal, ordinal, interval, and ratio scales. There are no interval or ratio scales in psychology. They don't exist. Nominal scales are not about quantities at all, they're just labels. So the only thing we're left is the ordinal scale. And so we should do something with that. And that's what we're trying to do here. So, so this in turn affects the interpretation of interactions, which is exactly Loftus' point many, many years ago. And monotonic linear regression can be used to determine if an interaction is non-removable, and therefore that an interaction also exists in theoretical quantity of interest. So I think if we take this up seriously, then it means a massive reduction in the number of papers that get published, because no longer will you be saying, oh, look, I found this little interaction. I think, therefore, I'm including this about memory or that about memory. You have to work a lot harder than that. So that's it. Thank you. And I'll take questions.
John, ratio scales, comment about Dunn-Lewis's process, please. As in, the demonstration that the choice axiom holds, then there's a strong utility function that is a ratio scale. And I have always tried to impress this on students as a quite remarkable thing, because we usually believe there are no ratio scales in psychology. I guess you might say, well, the Lewis choice axiom can be shifted unless it's applied, so it's not axiom.
So this would, yes, okay. So right. So Lisa's choice axiom turns out to be equivalent to a logistic link function. Right, if you do the math. And so I think that's a claim. Right? So what if that's true, then you're fine because you've discovered the correct instruction. If the data have that property, then I don't think there's any dispute with what we would say here. So if you apply the MLR to those data, it would come up with a set of an additive model and it'll show you that logistically function.
That's the logistic function that the rest of it is length function, exponential similarity. But I was just thinking of the original claim of the original proof in the choice data was, if you have the choice axiom holding, it's about consistency of preferences, versus small large sets, then it necessarily follows that you have the ratio of representation as a loose choice model representation of choice probabilities, and moreover that is unique up to a ratio, so you did the ratio scale, which is
Okay, yeah. Well, I thank you for that. I mean, I'll have to have another look at that and to see how that's being used. But I don't think that there would be any, as I said, any. It strikes me as very similar to what maybe we've had this discussion, but you have the same sort of argument in conjoint measurement, right? So you could say there is an underlying scale, ratio scale, or actually it's an integral scale, it's not a ratio scale, where certain properties hold, right? So you can test these relationships in data. The trouble is, of course, that it doesn't deal with error, so it's all idealized. So that's why. So I think I haven't stressed this, but I think what we're talking about is that the scale values that will emerge will be on an integral scale, not ratio. You have to add additional assumptions to make it on ratio scale because you have to put a zero somewhere and it has to be meaningful and so forth. But I will take your point. I will now think about that some more. Yes.
I feel like you could say almost never.
Almost. All right. I'll say almost never then. Fine. Andy.
Yeah, could you go back to the few screens back where back. No,
That one?
there. No. Oh, no, this is okay. Sorry. This is possibly a really dumb question. But so as far as I understand what you're doing is you're basically looking at the 8 orders that are consistent with additivity.
Yes.
And then doing a bunch of fancy things to see which of those fit best. Is that right?
Yeah.
So what if you're wrong and it's not actually additive? So I'm wondering about the errors that this could make, right? So like obviously your theoretical construct is wrong, but if you are wrong about that fundamental thing and the truth is not one of the 8 orders you're consistent with, does that, like, in what circumstances does that lead to the wrong conclusion about an interaction and so forth?
Okay, so the way to think of this is to say I want to show that these data are consistent with interaction on my construct. So at the very least I have to show that that's the case. So I'm going to assume that the construct is additive. If so, then it should fit these data. If it doesn't fit the data, then I've got evidence against the notion that additivity assumption was correct. If it does fit the data, then I've got no evidence, right? I'm just saying I don't know what the true situation is. It could well be interactive, but these data are not going to be the ones to tell me that.
What's the odds? You might say this never happens, but what are the odds of I get some data because it's not additive, some weird thing of data that of the 8 additive things, the best ones it fits are in an interaction. You see what I'm saying? So the test mistakenly says it's an interaction when in fact it's not an interaction because it's some bizarro thing that's in one of the other, the non-considered orders. Is that even a concern?
Well, I mean, a miracle could happen, right? So I think that's I mean, yeah, I mean, you could, I mean, what are you going to say? I mean, all you're doing is you're saying that there isn't enough evidence in these data. So if, I mean, you're talking about data that looks like an interaction, but it comes at,
Yeah,
but it's,
I think I'm not expressing myself
okay.
well. I'm talking about sort of data that best fits one of the non-8 things.
Yes.
Really, really well.
Oh, okay.
Right?
Yeah, yeah.
That's the true thing.
Yes.
Right?
Yes.
And it's not an interaction at all. It's some weirdo thing. I don't know what the other big things will be.
There'll be some interaction.
Yeah.
There'll have to be some interaction. Yeah.
But basically, because you're not looking at any of at that true thing, it is.
Yeah.
I'm talking about model misspacing.
Yeah. Okay. So if your data is good enough, and that's actually how the data is organized, then of course you would reject the additive ones because it won't fit those 8 ones any good. But if your data is schmuck, right, then of course there is one out there that fits really well. But now you're talking about model complexity, right? Because now you don't know a priori which of those is. So you're going to fit all 24 of these orders in this case, and one of them will fit really well. And then you've got another model which says, oh no, it's only this 8. And of course, now you've got different priors in that sense. And it fits okay. So now you've got to trade off complexity and everything else. So yeah, I mean that's.
But is that part of MLR?
No. It's at the moment it's straightforward frequentist. I'm just going to fit this model, and either I find evidence that it fits well or I reject its fit. I'm not doing model comparison like that. It's an interesting idea. I think that goes to the sort of more Bayesian approach of it all. That you have to, yeah. I honestly, I'm not steeped in Bayesian law sufficiently to say one way or the other, but that would be the way you'd start thinking about it. One of the advantages that I think about our approach is that because it's based on a bootstrap resampling, we're not making strong distributional assumptions about the data. And at the moment, I feel that's a good thing. There are shadows around that about whether the bootstrap is a good enough technique. But at the moment, that's the way we're dealing with it, because it's yeah. So, but I think I take your point, and it is that model complexity because I mean the other thing, of course, is that if your model says any of those 24 are possible, then you'll fit the data perfectly. Yeah. So that's the thing. Any other insightful comments that put me on the spot?
John, the relationship with Anderson's functional measurement theory, is clearly another kind of tack on this, which I remember when I was doing people like Dunn thought were it was supposed to be the kind of methodological way forward. And I think that's knows, right? Yes.
No, it's a bit of a dead end, that one. So this is an attempt to try and create additivity in the data. So and Norman Anderson, did a lot. The trouble was that it never really took off. And if you go back, you'll find a lot of papers by Norman Anderson citing Norman Anderson. He was making great claims about it. But it was all about trying to massage the data into an additive shape.
That was a sort of strong scientific a-priori view.
Yes.
If you had integrated simple relationships, and this was.
Yep. And there was multiple, and he contrasted that with multiplicative arrangements and so forth. So there's some. I mean, I've tried to look at it and tried to sort of think about what he was doing. I don't see there's a superficial resemblance. But one of the things that I would say is that when he makes the contrast between additive and multiplicative, they're just 2 different monotonic link functions. So there's no difference between the 2, none at all. But that's part. I mean, I think there's interesting work that can be done to actually see what kind of link functions emerge. If you strongly believe that the underlying model is additive. Or not even that. You just say, well, okay, I've done the analysis. The additive model fits really well with this link function. Why this link function? Where's that come from? Why is it like that? And I think there's interesting work to be done there. I have to say I'm barely scratched the surface on it. I've done a little bit of work with recognition memory, finding skewed functions. There's some other work you find if you ask people to make judgments about utility, then you do get these kind of logarithmic exponential functions. Not quite exponential, but they're kind of exponential. So that's interesting, I think, and I don't know where to go. So I'm just putting this out there. This is part of my putting it out there to say here's a technique which enables you to address the problems raised by Loftus, and it also tells you something interesting about your data. So have a crack. And
so how important is it that you restrict yourself to the cell means to be able to do something similar looking at distributions?
At the moment, we've packaged it as the cell means, but you can actually analyze it as an individual participant. You have models of participants. So you think of the participants as being a factor. You get into calculational problems, right? So these toy examples are great. As soon as you get up to about, so this study you have 4 cell means. Suppose you've got 20 participants. So that gives you basically gives you you have a design matrix with 80 columns or 80 rows, and number 3, 24 columns. That turns out to be a hefty analysis. This poor little laptop of mine starts smoking at that point. So you get into combinatorial problems, but in principle, that's exactly what you can do. You can do that.
Could you simplify that if you were able to assume that there were you didn't have to use all possible orderings, you could place constraints on the order of, say, A1, 2. So that only a subset of the ordering possible.
Yeah, that's an interesting suggestion. Yeah. Have we done that? Yeah, no, I think you're right. So how this works, and this is the is that you have to think about these orders as being part of the giant n-dimensional polytope. If an order, there's another order, there's another. They're all connected by a little this between a pair of binaries. If one order to the additive model is a subset. It turns out to be a connected subset. So as long as you find one, you start and do that very easily by doing the ANOVA, that gives you an answer. It puts you in there, and then you basically do a search. Start looking at what it's connected to. And then, right, any of those better? That's a bit better. I'll go over there, and it's the best first search. That's all. That's the sophistication of it all. And you keep doing this until you give up. Basically, you decide you've looked far enough. You're not improving your fit anymore. Although who knows what's around the next corner? There's always that risk. But you're right. I mean, if you were able to a priori limit yourself to a subset of that subset, then that would solve it. Now let me think. You've said that, and I'm trying to think if I've actually built that in. I think I'll have to take that on notice. I'll have to go back and see what I've done, because it's very similar to the work I have done on state trace and sign difference analysis does build that in. And it says we have an a priori expectation. This condition is bigger than this and this bigger than that. And so that limits your search. But it's a good point. I'll have to go back and really see which of my many versions is that or not. Are there any online questions actually? That's that. Yeah.
Okay. One easy question.
Okay.
Possibly. Is there a R package for this?
there's not an R package. There's an R program written by me in R. So this is on OSF. Can download it. Most of this work has been done in MATLAB. I'm an old reconstructed MATLAB guy. But there is a version that in R, not well written. I speak R with a terrible accent. Yeah, it's available, and I think there's a lot of smarter people out there than me who can play with it and try it out and see what it does. It's a lot of fun actually to analyze data this way and to see what it tells you, it's often quite surprising. So anyway, this is what I've been doing over COVID. Thank you very much.